So we'll start the session on chemical reaction and tracer gas. Professor Dheeraj Garg is from Shiv Nadar University, and he is one of our esteemed faculty partner of Open Forum Team FOSSEE. So over to you, Professor Dheeraj Garg.
Thank you very much, Payal, for the nice introduction. Namaskar, everyone. Welcome to this session. I hope so far you must have gained a lot of things related to CFD. So today I will take a special case, not special in the sense, some extension of CFD, what you have done so far. It is related to passive scalars and use of passive scalar as a chemical species, like tracer, and as a chemical reaction. How can you incorporate? So I understand many of you are not from chemical engineering background. So the idea is to give that we can use sometime from the mechanical perspective. We want to look how the mixing is going on in the system when there is a flow, and we want to look something like if there is a chemical reaction, how would you simulate it? So that's where the usage of passive scalar come into picture. This is what I will take. So let's start and let's see this. So you must have seen these equations in CFD. The first one, the equation that you are seeing in this, del rho phi by del t plus divergence rho phi u equal to divergence sigma grad phi plus s phi. So in this, each term has its meaning. You must have gone through this part in CFD so far. The first is the transient time dependent term. So phi is any property which is per unit mass. Okay. So we are looking through first term, the time variation in the system, that how this phi is changing with time. Then the second term is the convective term, how the thing is changing due to convection, due to the flow in the system, how it is changing with flow. The third term is related to the diffusion. So how as the molecular process, the diffusion is taking place, how the things are changing, how this property phi is changing due to diffusion in the system. Okay. And the last term is the source term. That means the property phi may be something which may be created, may be destroyed or being consumed within the system, irrespective of convection, diffusion, or time. So all these things, we assume that they are occurring independently, are not dependent on each other. So we are taking the total effect. So if you take the convective term on the right hand side, so convection, diffusion, and the source term, that means you can track how any property phi is changing within the system with respect to time, which is the outcome of this. So as you can see, so if you take any control volume where we say, okay, looking for the mass balance, for population balance, like in anything coming in minus out, anything entering the control volume, and it plus anything leaving the volume, plus generation in the system minus consumption of the system is equal to the accumulation of the thing in the system. So same thing, this will become like this. So incoming and outgoing are taken care through the convection and diffusion, and generation and consumption is taken through the source term S phi. Now, this is the generalized way of writing this equation. So when phi is equal to 1, this will convert into the conservation of mass. When we take phi equal to u here is the one component of velocity ux. Somebody, if to avoid confusion, you can see it as a ux. So for single term, this will be, it will easily convert into the equation for conservation of momentum. And when phi is taken to be I, which is internal energy, you can derive easily the equation for the conservation of energy. So idea of generalization, that in all the three systems, conservation of mass, momentum, energy, which is on which the whole CFD is based, we see the few generalized terms and we build our coding and calculation based on this generalized form. So this equation is that. Now, with this phi, as I have already said, phi is any property per unit mass. And this phi can be used as a passive scalar. So far we have not taken anything else. So like if we want to use chemical species, how would you simulate where it will lie? Because conservation of mass leads to density, momentum is velocity, and conservation of energy will lead to the temperature form, even though the temperature can also be taken as scalar and sometimes it is used as a scalar, passive scalar. So the natural question is asked, what is passive scalar? So much we have discussed. What exactly is the physical meaning of passive scalar? So let's say any property is phi, okay? So in a given volume, control volume, there is a property phi whose value you know for given x, y, z, and t. That means time and space, you know every property. It is varying in the time and space. And you know in the beginning, let's say. Now, if you are moving from one point to another, let's say x1, y1, z1, and at time t1 to x1, x2, y2, z2, and time t2. So as you are moving along the line and you want to know what is the variation of phi with respect to this. So you take the total derivative with respect to time. So this is the derivation you will get, that you need to differentiate this phi along the line with respect to all the variables in space and time. So naturally you can see the total phi variation of phi with respect to time will be coming, the contribution will be coming for the variation in the del phi by del x. That means as you are moving in, so the variation in x, the gradient in x, gradient in y, gradient in z, and in time. But along with gradient in phi, you will see another term del x by del t. Okay. Similarly, del phi by del y into del y by del t. So what is del y by del t and what is del x by del t? Somebody may say, what is this physically corresponds to? Distance by time?
Velocity.
Absolutely, absolutely. So that means we are not only dependent on the gradient, which may be existing, but also how fast we are moving in that direction. Now, this velocity dx by dt, when you are moving, when it is same as the substance velocity in which you are moving, okay? So that will become, that dx by dt will become same as u. So here, the importance, what you should see is that the phi can have its own velocity of varying. So take an example that you are, so as you can see in different books also, take an example of a boat. If you are sitting in a boat and you are in a river, it's a flowing. So if the boat is driving its own mechanism and moving in the river, let's say against the flow or in any direction in the boat, in the river, so its velocity dx by dt, dy by dt, dz by dt would be different from the river flow rate, river velocity at that point. So the velocity will be different, and hence this dx by dt, dy by dt will correspond to the boat. But let's say that boat is still and is moved along the flow as the river is flowing downstream or wherever, it is moving along with the river. So if you want to calculate velocity, how it is moving, that means you can say that velocity dx by dt is same as the local velocity of the river at that point, which is same as u, dy by dt is same as v, and dz by dt same as w. So only when the substance velocity in which the property is there and its own velocity becomes same, then then the same derivative is called as substantial derivative. So here the meaning is that the scalar is not affecting local velocity. Okay, it's not affecting the surrounding velocity, it is moving along the local velocity. It is guided by the local velocity. And this is very important to understand, because many times we do several experiments, like you are dropping a ball in the water, let's say, or oil or fluid. Now, if the ball is large enough, it may affect the local flow rates, local velocity distribution, local pattern. So, can you take it as a passive? Answer is no. Okay. because it will have its own velocities, its own movement. So this assumption is very important to be clarified, that when a substance which you are taking does not affect the local flows, so the its own size should not be large enough that it affects the local velocities, then only you can consider it as a passive scalar.
Sir, I want to ask just one question. It
Yeah.
depends on the flow field.
Huh?
It depends on the flow field where the air is flowing or
Huh?
some water is flowing.
Huh?
So how I will connect with the physical world, because it will take the, like river is flowing. So
Huh?
river having some velocity,
Right?
and we move with the boat, and we have
Okay.
some velocity with the river water. So
Yes.
how I will connect with this equation with this physical phenomena? I can't get it.
Okay. So let's say you are having a boat and you are on the river. River have its own velocity pattern, right? Profile is there at every point, right?
Yes, sir.
Okay. Now, if the boat is not powered by its own mechanism, and let's say it is light enough, okay, so that it is following its, so let's say raft boats are there, let's say, and the flows are large. So how do you expect raft boat will move? It will move along the flow, right? I'm just simplifying the, although it is large enough to say, but from that level you can see the raft boat, if you are taking, if the raft boat, you are not rafting at all, it will move along the flow, right?
Okay, sir. Okay.
So if you want to determine how will it go, you simply see the flow of the river and you see how will it go, right?
Yes, sir. If we stand outside the river, just we are
Yes.
taking the local derivative.
That is, yeah, of course. You are looking from outside the river, so you are seeing it, right?
Yes, yes.
So in that case, your velocity or the raft boat velocity moment is same as the flow of the river, right? In that case,
Yes, sir.
dx by dt of the raft and the u of the river will be same.
Yes, sir.
Now, if you say you start rafting,
Okay, sir.
so in that case, your velocity of the raft boat will be different from the river velocity.
Yes, sir.
That means this dx by dt for the raft is not same as u. So dx by
Before.
dt needs to be calculated separately.
Okay.
So that is what is the idea, that when it is same as u, then it is considered as a passive scalar. Then you do not have to calculate its velocity separately. The local velocity of the substance itself will be used automatically for this, and then it becomes a passive scalar. Then you can use that thing for visualization. So people have done what? They have dropped several small plastic balls or toys. They can float on the river and they look how the river is going from one point to another. So when they observe some plastic, the same plastic ball somewhere else, to say figure out, okay, it must have come from this river because we have dropped it there and we are seeing. So this is the same idea here to that
Okay, sir.
extent, right?
Okay, sir. So just we are focusing on the velocity of river, like flow field. Main agenda of this equation is the flow field, uh,
Main
which I am
agenda of this is
understanding.
that the flow field need not to be calculated separately. The interaction
Oh,
between the scalar and the field and the substance is, well, the interaction is neutral in the sense it is not affecting this. So that's why if you already have a flow field, you do not have to
yes.
recalculate it.
Okay. Just we
Okay.
combine two components.
So that component directly comes from the flow field itself, and that's what you will see in tutorial, that the flow field is already calculated and you are imposing the scalar. So that's why in post-processing, now new softwares have the technique of injecting particles, neutral particles, to see
Yes,
the
yes, sir. Sir, yes, sir.
flow field also.
Oh,
Okay.
thank you, sir. Thank. Oh,
Should we move forward?
Yes, sir.
Okay, okay. So please feel free to contact or ask question whenever you have doubt. Hana? Okay. So we will take several cases which are practical importance and understanding to you. So the first one is the tracer injection with uniform inlet velocity. Just to check to understand the concept, one of the thing that you can use a tracer. Now tracer is a chemical species like dye, potassium iodide is there. So there are several things you can use and you can actually simulate in the CFD. Okay. So how would you inject? So you need to see which properties you are going to use in the system. So this is the basic equation to start with. Okay. We have taken, now we have to see what are the things we need in this and what are the things we don't need. So when we are taking any tracer, let's assume that that tracer should not be diffusive tracer. So many of you must have done the very simple experiment of showing the transition from laminar to turbulent using a die. So in that die, it's a natural assumption that the die is neutrally buoyant so that it remains at the same horizontal level where it is injected. And we also assume that it should not be diffusive. Otherwise, it will just like an ink diffuse through the fluid, it will diffuse and it will cover the whole cross section. So if we look from that, so if you are not assuming it's any diffusion, so which term should become zero? Can somebody guess or tell me?
Divergence of delta grade phi.
Right. So the third term is the diffusion term. So this will become zero. To make it zero, we are not making grad phi, but the sigma of that which is corresponding to diffusion, molecular diffusion, will take it as a zero. Now in some software, this value zero may not be taken directly. It does not accept zero. So what we do, we take it value 10 to the power minus 30 or even smaller to overcome this issue. Sometimes they do not take absolute zero as the value. So taking as minus 10 to the power minus 30 or even lesser, this will do. So this is practically becoming zero. Now, since the tracer is there, there is no possibility of source term. That means it cannot be generated and it cannot be consumed. So the fourth term will also become zero. So this will lead to this term. So what we are looking in the so if the variation is the so if you are looking for an unsteady state condition, then the only two terms, del phi, the first term time variation, unsteady, and the convective term is there. And this is the equation which will be simulated. Now, in this case, there is a possibility your problem may be time independent. That means steady state. Then the first term will also become zero. So the only thing that will be solved by the solver is the second term, that equal to zero. So it is up to you what type of analysis you want to do. So for a tracer, chemical tracer, so phi is the chemical species. So generally what we do, since it's we are not interested in actual concentration or actual values, we denote it as a phi equal to 1. That means it's a maximum concentration and the minimum concentration would be 0. So we simply inject at the inlet, okay, with the boundary condition as phi equal to 1, and we observe how it is varying with time and space across the control volume. Okay. So if you are looking and interested in the time variation, how it is from the beginning of the injection to it reaches steady state, you can use this part where del by del t term is there. And if you remove this one, you will get the steady state analysis. Now there is another interesting thing is that, as you will know, as you are already aware, if you continue any transient analysis for a long time and it is going to approach equilibrium, so ultimately you will get a steady state analysis. So there are sometimes two different ways of doing the thing. Sometimes steady state simulation is difficult. So people have used transient analysis and running for long time. So the last time step or longer time step, whatever the solution you are getting is technically steady state solution. So it can be an engineering way of solving the same problem in a different way if the solver works easily in unsteady state. So far, so good for this part.
Sir, I have one question.
Yes.
So in the last equation, so if there are no transient component,
Right.
so that means the distribution of tracer will be just equivalent to the distribution of velocity, right? I mean, qualitatively. Is it not the scenario?
Distribution of
The tracer you will get in steady state context, it will be quite similar to the distribution of your velocity wave.
Maybe, may not be, not necessarily.
Okay.
That's what is the thing, but so it may give that similar thing you may be visualizing. It should actually follow the same thing. So yes, in some cases you may get that thing. In other case, this may not be. So for example, let's say when you are injecting, since it is the local velocity, so let's say you are doing steady state analysis or any doesn't matter. Let's say they are dead pockets.
Hmm.
So what will happen when you inject the velocity? When you inject the tracer, so it will cover those area according to the velocity, like absolutely like you are saying. So if there are dead pockets, the tracer may move, may not move in those pockets. So that's where you can realize, you can see.
Okay.
So yes, sometime it may be similar to that, what you're saying, absolutely correct.
Okay.
So the same technique actually is used for visualization also. So now we have visualization techniques. So post-processing, if you are looking, so same thing can be used there also without actually injecting tracer like that.
Okay. Thank you.
Okay. So
Sir, I have a question.
yes,
Sir, what is the objective of this dye injection? What do we need to find?
right. So the thing is, sometime you want to visualize how mixing is occurring. Is there any dead pocket in the geometry? How the things are moving from one point to another. You want to visualize what is happening inside, right?
But as you told, there is no diffusion.
There's no diffusion, so you are looking only the convective aspect. So like say in the bigger size equipment, let's say the flow equipments are there, bigger size industrial scale. You want to see how the pattern of mixing is there, how the things are moving from one point. So you are sometime only interested in convective aspect because the system is large enough where you can safely neglect the diffusion. Okay. So if you want to see how the things will move, then you simply have to use this part. So if you are simulating, if you want to simulate mixing, let's say you are bringing two different chemical and you want to see how fast it will move and how they are mixing together, then this is the equation actually in the background where diffusion is not considered. There is no source term. So you are simply simulating mixing, right? So now the application is many people bring like, okay, we have devised this thing. This has improved mixing. Now, how would you look at that if you want to evaluate? So this is where you can do that. You can take a scalar at the inlet, you inject it. Okay. Now, in that case, to see what people do is they inject partially because you want to simulate mixing. If you are already giving the complete bore injection, then everywhere is the tracer. So you inject partially. So let's say 30% cut or some particular portion of at some point where injection would be there, and you see how the tracer is now moving along the flow, and at the end, ultimately, how much it is appearing across the cross section. And then you can evaluate how the mixing is occurring throughout. Similarly, you can use it for seeing the mixing in heat exchangers. See how heat exchanger. So there may be, so that is the additional complexity you can use, see how heating or cooling is affecting mixing in a given system. Right?
Or open heat exchanger.
Open, close, but this is the equation. So if you see temperature is there, so the it is coupling with the temperature is right. Rho density is changing with temperature or not, and U is changing through the mass momentum transfer is coming from there. So automatically it will come. So okay. So another thing I would say, as you might have seen, any system as we have seen previous equations, unless density and viscosity are changing, the systems are considered decoupled. Decoupled means they can be sold individually. Okay, so they need not to be sold simultaneously. But if the density is changing and the viscosity is changing, that means they are coupled system. That means you have to solve them simultaneously. You cannot evaluate them independently. Okay, so let's say there is a chemical reaction or there is a heat exchanger, temperature is changing. Now, if because of change in temperature, density and viscosities are changing significantly, then you cannot assume that the profile, velocity profile would remain for isothermal condition, and for non-isothermal, it will remain same. So it will change accordingly. So far, is it clear related to this part?
Yes, sir. So for two stream are mixing, so are we going to find entrainment ratio or kind of physical quantity?
So so in this particular today's topic, we are trying to make you understand how to do it, how to do the injection of tracer. Then the application like entrainment you want to do, those things you can easily extend to your requirement. Once you are aware how to do it on the code, then
Hmm.
everybody can do it for their own interest. Okay,
Yes, sir.
so that's the idea. Okay, let's move further. So the another important aspect and practical application of this is the residence time distribution. So in this, we will be showing in the tutorial with the parabolic inlet velocity. Parabolic inlet velocity is basically corresponding to the laminar flow, but it can be done with the turbulent flow too. So the what is residence time distribution? Residence time distribution is for the visualizing how good is the mixing inside the how the time distribution of different particle is varying within the system. Okay, so for that, so same equation is applicable. The except that the boundary condition now would be the inlet velocity should not be flat, but the parabolic velocity profile. Okay, that's the only difference. So the residence time distribution is special application of the same mixing characteristic with the distribution velocity distribution at the inlet should be fully Taylor flow. So if the flow is laminar, it should be parabolic. If it is a turbulent, accordingly, flow profile can be given at the inlet. So is anybody of you aware of residence time distribution concept?
Yes, sir.
Okay, that's good. So one of the important thing is residence time distribution concept is always a transient analysis. So del pi delta term would always be there. So in that, what you do, you inject at the beginning full bore. So here the injection is always full bore, phi is always 1. And at the outlet, you look first appearance of the phi, if the value of y is changing from 0 to, and how it is changing to 1, depending on the continuous injection or impulse injection. So that's a specific example of this. So so if you continue to give phi equal to 1, maintaining in the code, this is the continuous injection step in or step input. If you apply the delta function that phi equal to 1 and in the next step it becomes 0, it will incorporate the impulse injection. So far so good?
Sir, I want to ask one question.
Yes.
So there is 5. If we
Yes.
take the 5 value equals to 1,
Phi
so
value
how
goes
we will
to,
calculate the continuity equation or some other equation, because 5 value is varying.
yes.
So I'm not connected. If you
Okay,
elaborate.
so as I said, since this is passive scalar, so your flow distribution, pressure distribution, everything is already established. So they are not touched and you don't require to touch them at all. You are only solving for phi. Is this
Okay, sir.
clear? So the
Yes, sir.
thing is like you are running initially for the velocity distribution, you are running simulation without phi, let's say. No chemical injection before, no tracers, you are not simulating anything except that you are running for your velocity profile. So once it is obtained, now you are taking the last simulation as the initial condition for this. That means it is already settled. You are already having obtained the final distribution. So when the system will solve, it will not solve for pressure and velocity because it is already solved and it is not getting affected because of the injection of phi, because phi is passive scalar. Had the phi not been passive scalar, that means it will affect your local velocity. That means it will affect your pressure calculation again.
Okay, sir. Okay.
So you do not need to worry about the pressure and velocity. Since it's already there, you are only looking at the injection of the tracer and it is only solving for phi.
Okay. If I'm injection velocity taking 1 meter per second,
whatever it may be, whatever velocity profile is there, you just has to impose it there.
And because there is already mentioned the equation of pressure and velocity, then by default I am taking the phi equals to 1 meter per second.
No, phi is not velocity. Phi could be any property. Phi is not velocity. It is u which is velocity.
So
Phi
phi
is
is a general property which is like
so let's say
an
okay. So I got the point. So let's say generally what is phi is generally let's say chemical species. So we talk about the molar concentration. So let's say phi is potassium iodide. So you say okay, the molar concentration is 10 mole per liter, something like that. So rho phi is 10 mole per liter. Okay. So now the thing is you have an option to solve phi as the concentration value,
yes sir.
or you can simply give the phi as 1, where phi equal to 1 correspond to 10 mole per liter. So what if you find in any of the mesh, you find phi equal to 0.5. So what should be the value of concentration in that? Half of the total concentration, right?
Yes sir.
So that way you can simplify. That's why we want to simplify the task. So normal cases, when see we have no reaction, nothing else is there, where we are only interested in the distribution. So phi
Yes,
equal to 1 will suffice, where phi is equal to 1 correspond to the maximum concentration, whatever it may be. And phi equal to 0 means no concentration, and the correspondence between phi concentration and the phi 1 to 0 value is linear. That means 1 correspond to C node, 0 correspond to C, 0.5 will correspond to 0.5 C node.
Okay, sir. I got the point, sir. Thank you,
Right?
sir. Thank you.
So now we are, that does not affect our calculation. Okay.
Yes, sir. Yes, sir.
Okay, good. So let's move to the next. So the next is the case we will take to make the understanding half bore injection with zero diffusion. Okay. So in this, what we'll do in the half bore injection is same equation like the previous case. That means del phi, del by del t and the convective term. And we will see this that, okay, if we are injecting half bore and there is no diffusion, what do you expect the liquid to move? How should it move? And we are taking the flow to be laminar. So this is the idea that you want to visualize, that if we are giving only, let's say, upper half or lower half, you are injecting a tracer and there is no diffusion. So there should be, how do you expect the interface to be? Can you visualize? There is a straight tube, let's say.
Stratified.
Pardon me?
Stratified interface.
No, it will not be stratified. It will be sharp interface because diffusion is not there. So, okay, I should have given the background. So let's say there is a cylindrical flow. Cylinder is there. And there is a laminar flow. So in the laminar flow, as you are aware, is a parabolic velocity profile. So in the lower half, we are injecting lower or upper half, we are injecting the tracer. So since the tracer is non-diffusive, okay, so will it diffuse to the lower half or the other half in which it is not injected?
It will not diffuse, I think.
It will not diffuse. The thing is, the idea of showing is that laminar flow is stratified flow, as somebody rightly pointed out. So there is no radial mixing because of convection. So the only way it can mix radially is through diffusion. And that's what we want to show you, that what is the importance of diffusion. So if you are injecting a tracer in the one half of the cylindrical flow with the laminar flow, and if we are simulating as no diffusion, we will see it will simply inject it and will cover the one half of the cylinder without even moving to another half. So there will be sharp interface of the tracer at the middle with no diffusion. But on the other hand, if there is a diffusion, so what should happen in that case? If the die or the tracer is now having diffusion significant enough, then what will happen?
So turbulence may be dominant.
Turbulence become dominant now. See, it will not affect your velocity profile. What I'm trying to say, that when you are injecting tracer and it can diffuse also. So what will it do is in a laminar flow, in the cylindrical flow, if you are injecting in one half of the cylinder, because of diffusion, the interface will not remain sharp because it will see that other side there is no tracer is there. So it will start diffusing to the other side. And if you continue to stay it for longer, it may cover the whole cross section also. And that is the basic idea of using in the micro reactors. Why many of you are aware of micro reactor and micro devices? Many of you are aware of that?
Yes, sir.
So why do we use micro reactor and micro devices?
Sir, we are working on the micro channel where we calculate the bubble diffusion.
Right? So the thing is, in the micro channels on those devices, people are now working. The radial cross section is in microns or milli. Why we do that? So that the diffusion in radial direction becomes significant. The contribution of radial direction, diffusion in radial direction becomes significant. And you can see here also in the tutorial that most of the time in the micro reactors we have laminar flow. So we do not expect the laminar flow, the radial diffusion, radial mixing, but still mixing is quite good in radial direction because of diffusion. Okay, so the question is, how would you incorporate diffusion? So this brings to this part. Since the source term is 0, now we have the convection term and also the diffusion term. So these three terms needs to be there in the equation, in the code, and that will take care of the diffusion part. So having this incorporated in this third part will include the diffusion. Okay?
Yes, yes.
Okay, I am seeing two questions, one from the Vipin, by phi equal to 1 in equation, this becomes mass conservation equation for tracer. Okay, so this part, what I was telling actually in the beginning, by taking phi equal to 1, the only thing I am trying to imply that, and this is the simplified way of, actually, that is a simplifying way of converting the equation into coding. That you can convert the code if you are writing code, you can take a modular approach, as you will see in the open form also, where you know that there are common elements, so they can easily be converted. So you need not to write different codes for implementing conservation of mass, momentum, energy. They can all be implemented using similar modules. Okay, so those parts are there. So phi does not mean that when I take phi equal to 1, it will become conservation of mass. What I was saying is that it was a simplified way of writing all the three conservation laws. And this is the technique to simplify the coding, that you do not need to write separate code for conservation of mass, separate code for conservation of momentum, separate code for conservation of energy, but rather you can use the common terms, and accordingly you can convert and modulate slightly to accommodate all the different conservation laws. Is this clear, Vipul? I hope this is clear. And second is from Sibin. If we are giving continuous injection at a point in a flow field, eventually the tracer will cover the entire flow field, right? Exactly, absolutely. This exactly is the point in the RTD, residence time distribution. So the moment it covers the whole channel completely, you will get phi equal to 1 throughout the cross section, and that's where you need to stop your RTD analysis. So that exactly is the point. The RTD analysis is always transient. It cannot be steady state because eventually it will cover the whole cross section throughout the system. So you won't see any variation. So RTD analysis, residence time distribution analysis, is always a transient analysis, and it continues till, as you have rightly figured out, till it covers the whole thing, because beyond that you won't see any variation. So very good question. Thanks to bring it.
Sir, one more question. So we
Yeah.
have to give continuous injection, right? Not pulsating injection. pulse
Okay. So
injection.
continuous injection means phi equal to 1. If you are specifying, it automatically becomes continuous injection. Because the boundary condition will continuously see phi equal to 1, right? That means it is continuously seeing. Whenever you are fixing some value, it automatically becomes continuous injection. For example, you are specifying velocity at the inlet. Since it is not changing, that itself means there is a continuous flow, right?
Okay.
So when you are specifying phi equal to 1, it means the tracer is coming continuously at the same concentration. Unless
Okay.
you give some formula to change it with time. That after this, it change to this or this. Otherwise, it will continuously coming injecting at the same concentration.
So we have to add tracer, like you said, 10 moles per liter, like that.
Uh-huh.
Initially, we have to give a concentration value.
So that's what I said. The thing is, if there is no reaction, and there is no non-linear term in terms of, let's say, diffusion, so phi equal to 1 is a good way to overcome the issue of absolute values of concentration. Because there is a linear correspondence between phi equal to 1 and phi equal to C naught. So let's say the C naught is 0.002 mole per liter, right?
Okay.
So it's a difficulty in getting the data.
Okay.
Well, you are putting 0.002, but putting it as phi equal to 1 is easy to visualize the thing. Anyway, whenever phi equal to 1 is there, 0.002, it means 0.002. When phi equal to 0.5, it means 0.001.
Okay.
So it's your choice. You can feed it as 0.002, and it's your choice, feed it as a 1 till there is no reaction. In the reaction, absolute values are important.
Okay.
But non-reaction, that is not there, then this will work perfectly fine. This system will work perfectly fine. If you actually need some values, you can always multiply the whole values of phi from 0 to 1 by the C naught. You will get in terms of C concentration.
Okay.
So far, so good.
Yes, sir.
Okay. So now let's introduce to the chemical reaction. So when you want to introduce chemical reaction, many of you have studied chemistry, basic chemistry. So how can you use this passive scalar for introducing chemical reaction? Okay. So in the chemical reaction, what you already know is, let's say Ra equal to minus Kca. This is the basic. A is reacting to B, giving you Ra equal to rate of reaction is minus Kca. Okay. K is the kinetic rate coefficient, Ca is the concentration. Now here, it's a linear variation. So how would you implement this in the batch reactor? So here you look. Now phi is the reactant. Okay. So you want to simulate batch reactor. So since it's a batch reactor, there is no flow. So the convective term will become 0. Now, again, we are saying it's a homogeneously mixed. So diffusion term will also become 0. So ultimately, this will reduce to this form. So if you look closely, if you replace this term with the reaction concentration, so the Ra term, if you remember, dCA by dt. So left term will become dCA by dt, and the right term will become minus Kc. So what I'm trying to say is, you will rederive the same equation from this by removing convective and diffusion term, and this way you can simply simulate dCA by dt equal to minus Kca, or any complicated reaction term equation that is there on the right hand side. So that part will become the source term, and the left hand side is the reaction rate term. So this is how you can simulate. So if you want to implement reaction, so what we do is we go in a step-by-step manner. First of all, we need to implement like this. So source term we have to define, and the source term would be the reaction term. Okay, and we make the velocity 0, we make the diffusion 0, and we actually simulate only for the single mesh, because we are not looking for the convection and diffusion. And we simply integrate, and we want to verify whether we are getting the same result as the result would have come theoretically. So when this is coming correct, we accept the result that now it is, the coding is correct for the batch reactor. We now want to integrate for plug flow. So that moves to the next is the plug flow. So in plug flow, what happens is the velocity profiles remains flat throughout. This is a theoretical concept. So plug flow is the batch reactor in the motion. So that means time aspect, what we were looking there in time, here it becomes in the space. So if there is a cylindrical flow from left to right, if the velocity pattern, velocity, inlet velocity is flat. So if the length is, let's say 1 meter and the flat velocity profile is 1 meter per second. So every particle which is entering at the left will exit at the right at the one after exactly 1 second. So residence time in the system will be absolutely 1 second for each particle. So this is the next level of integration. May you want to check, okay, S5 we have integrated correctly for single cell. Now I want to check it for my flow condition. Now again, diffusion term will be neglected, okay, and convection term will be introduced. So this is where the complexity will come. So we want to see, is it working with the plug flow or not, and am I getting any correct result or not? Because in plug flow, I know what should, based on the residence time, I know what should be the value at the outlet. So this is the second level of movement of implementing the chemical reaction. So S5 is there. Now we added convection also. So we have, so from time derivative term and source term, we have added the convection now. So once we are able to do this, once we are able to get this form that it is getting correct result, now you can go for actual condition. So again here we have shown one tutorial for you that there is a reaction only in the upper half or one half with the source term, but there is no diffusion. So from this equation, what we are going to do is this portion alone. So if you remember, we have taken the half bore injection with zero diffusion, but now there is a source term. So now understand one thing is that for source term, when I say for reactant, it will be minus, and for the products, it will be positive. Okay. So this is the equation that will be implemented for this. And again, since it is with zero diffusion, we should not expect anything diffusing from the one half to another. But if there is a diffusion, then we are actually implementing this whole equation. And we should see that as the reaction is proceeding, there should be some diffusion also. And how will it affect your overall changes that you will see in the tracer? The only thing I'm saying, the equation remains same. This whole equation remains same, but using different parts, it adds different meaning, and you can use it for different physical conditions. Then the last module, the last tutorial that we will give you, that you will do is scalar 1 and scalar 2 gives scalar 3. What is that meaning? Let's say A plus B giving you C. That means two reactants are there. And this is the very much important condition for chemical reaction. People are dealing that you add two chemicals, you want to mix and you want to react and see how things are changing. There can be complex reaction. Okay. So earlier you were looking only at adding A and B and mixing alone. Let's say there is no reaction. So whatever you have done previously, absolutely useful for you. But if you want to go one step ahead and you want to simulate reaction, so there is a mixing, there is a reaction happening. So the same equation you have used, now you are using two scalars. So A and B are the reactants, so their source term would be negative. And scalar 3 is a product, their source term would be positive. And the same equation will be applicable for 1, 2, and 3. So in this case, depending if you are, let's say in tutorial, we have taken upper one half for the scalar 1, one half for the scalar 2. So the boundary conditions, what will be the boundary condition? So let at the inlet. So phi A will be 1 for one half. Phi B in that half will be 0. Phi C in that half will be 0. Phi A in the second half, where B is injected, will be 0. Phi B will be 1 and phi C will be 0. So technically you are injecting A from one half and B from second half, and C you are not injecting, it is getting produced due to the reaction. And you will see the two cases with or without diffusion also. You will see how things are changing accordingly. So that's all from my side. for the chemical reaction and this. Is there any question further? You please feel free to ask.
Sir, if we want to find the mixing time in a cylindrical reactor, you can say.
Okay.
So we have to give tracer from a particular point, right? Continuously inject.
Okay.
And then the initial concentration will be, how will you quantify it? Your final concentration should be maximum, right? So how would you?
So in that, see again, since you are not looking for reaction, right? Only
Yes,
mixing,
yes.
you are
Yeah,
interested in
mixing intensity.
So again, you can take phi equal to 1. Simple.
Okay.
So doesn't
Ah.
matter, you inject phi equal to 1 and you can calculate beforehand, okay, I am injecting this thing. So let's say if you are adding only a small amount,
Okay.
right?
How will you quantify that small amount? That's my point.
That's what I'm coming to. So there are two things. So one is continuous injection.
Okay.
So when you are injecting continuously, as one person already pointed out, ultimately everything will be reached to the maximum concentration, right?
Yeah.
So that means in the physical way, you know that if you are continuously adding something in a given volume, it will reach to the same as the maximum concentration. So the final steady state condition would be phi equal to 1 everywhere, right?
Yes, yes.
Right. Now the second part is, let's say you add small amount. Okay.
Okay.
You add just a small amount and you want to see how it is mixing and what will be the final concentration, right?
Yes.
Right. So let's say simple basic calculation. Let's say there's a 10-liter tank and you had 1 liter. Let's say 9-liter tank and you had 1 liter of one concentration. So in the initial, in 9 liter, there was 0 concentration and you had 1 liter with the C node.
Okay.
What is, if they're completely mixing, what should be the final concentration? It will be 1 by 10.
1 by 10, yeah.
Right? So if I go with phi equal to 1 liter of that, and I know 9 liter I'm adding. So I know by analytical calculation that the final complete mixing, if that is there, the phi everywhere should become 0.1.
Okay. Yes,
that is the desirable condition I'm looking at.
Yes.
Now, when you inject phi equal to 1 with the similar quantity you inject and make it accordingly, what will happen is phi will vary throughout. Somewhere it will be 0, somewhere it will be 1. It will vary from 0 to 1 various places. Now it is your choice where to stop, and you can track the quantity, how it is changing and where to stop. So it may reach 0.1 everywhere after certain time, or it may take infinite time. So based on your analysis or requirement, you can stop anywhere with reaching to this value, it taking this much time and that. Again, second part, if you are taking tracer to be diffusive or non-diffusive, it may again affect your final, because if the tracer is diffusing, then also the final concentration would be 0.1 only. Only thing is the mixing time will change, because now diffusion is also assisting in complete mixing.
Time will be less, right?
So time will be less. So point I'm saying is, how would you know what will be the final? You can calculate beforehand.
Okay.
And the thing is, you can verify your simulation that it should not be more than that uniformly throughout, or less than that. It is not physically possible. So if something is happening like that, that means something numerically wrong, or some errors you have made somewhere. So one should also be aware of the thing that you should not see phi should not go to more than 1 in case there is no generation or consumption. So when there is no source term, phi cannot go more than 1. And so this is the another important aspect of using phi equal to 1, because in the case when there is no reaction, no source term, because then you easily track that phi can never be more than 1 and phi can never be less than 0. Because when you use absolute values, you may be tricked thinking ki phi may change. Okay, 0.002 we took and now it is 0.0021, maybe somewhere something like that generated something. But phi equal to 1 and 0, the importance of no source term is that it can never physically be more than 1 for any reason, and less than 0, the only possibility is there's some error or some numerical diffusion or some numerical error. So that way you can easily figure out something is going wrong in the system or not. Your calculations are going in the right direction or not.
Okay.
Anybody else? Any other question?
Hello, I have one question.
Yeah, please.
Sir, it's related to application. Can we also simulate corrosion activities in OpenFOAM? If not, then what is the, based on your experience, what are the software that is available in the market where we can simulate the corrosion?
So I will give a generalized answer. So
Yes.
anything that you want to simulate is ultimately you are reducing to mathematical model,
Okay.
right? So let's say you want to simulate corrosion, somebody wants to simulate acoustics. People see it as a non-related at all. But at the end of the day, what you are doing in this software, it's a solver, right?
Yes.
What it is solving, it's solving ODE or PDE, partial
Yes.
differential equation. Now, what is that PDE or ODE corresponding to? Some conservation law, some mathematical model.
Yes.
So the idea of OpenFOAM or any other software that you will use, okay, freeware or commercial, they all are solving the equations.
Hmm.
So
Okay.
if you are saying it's a corrosion, you want to say, okay, fine, but how would system know it's corrosion? That means
Yeah.
you are writing some mathematical model, some
Mathematical
equation.
model. Yes.
So the moment you have equation, so you can always use this software or another.
Okay.
The only difference OpenFOAM compared to another is that you can write your own equation if that is not existing earlier.
Okay.
And other software, what they do, so they make module like in console, they offer this module. But at the back end of the module, they have written equations for the same thing. It
Okay.
becomes user friendly because they have done the equation modeling part. But if, and you have to pay for it.
Yeah.
Let's say you
Right.
don't have money to pay for the same, you can write down those same equations, use OpenFOAM, convert those equation into that coding part and run it. As simple as that.
Okay.
So it is not that I am saying it's restricted. The only thing is you have to first figure out the mathematical form. You must have the mathematical model and then you can go ahead. So there is absolutely no restriction. Only thing is you have to work out what is that mathematical form you need to solve.
Okay. Clear.
You can do that. You can do that.
Okay.
Right. So benefit is that they are so for certain cases, some modules are inbuilt. So that may be of help that for this you need not to write your whole model yourself. That is the only difference different software offer. They have some inbuilt features. So for particular case, you don't have to write your own equation complete setup for yourself. You just take and refer to that. That may simplify the thing. Otherwise, you can write your own equation. That's the only thing. So as you will use OpenFOAM, you will realize you can always check on the internet whether somebody has already worked in this area in OpenFOAM. So it is generalized for everyone whosoever want to use for the OpenFOAM for the particular usage. You can check it online that if somebody has worked on that. If yes, you can refer to that work and may see what are the similarity or differences. But if that is not there, don't get disheartened. You just write down the equations, see the mathematical model available with you. You can write same thing in the OpenFOAM code. It allows you complete flexibility that you can write the same code in the OpenFOAM and you can run it. And you can always take FOSSEE help to help you in solving it out. Any other question, please? Okay, so if there's no further question, I just tell there will be tutorial session by John. He has made several modules as we have discussed. He will take it up one by one. One of the important aspect is that the flow profiles are already obtained. So as we have already discussed, since it's a passive scalar, you don't need to work out on the velocity profile directly. I mean, you can obtain them beforehand also. So in all the cases, you are not solving for velocity. So the last velocity profile is taken as the initial solution for the current case, and you are only solving for phi. So I hope you will understand much better when you will go through the tutorials. And in all of them, you can play with the values and see the differences that are coming. That will give you much better idea of the concepts. They are simple tutorials. but you can play with the values like kinetic rate coefficient, source term. You can change the power of the source term, and you can play and see different results. That's the idea, that you can easily play with the things. With the same structure, you can implement different physical aspects. So like tracer, reaction, and you can make the things as complicated as possible to simulate the real world problem. So with that, I conclude my talk.
Okay, so with this, we conclude the theory session of this section of the workshop.
Okay then, thanks Payal.
Yes, thank you so much, sir.